Good afternoon to all of you. Thank you for joining. It's for me a great pleasure to present the speaker of the next MoD lecture today, François Charton. François is working in Meta in Paris, and he has developed a very bright and non-standard career in science. He will tell you maybe more about his own parcours. He was a student, let me start from the very beginning. He was a student in École Polytechnique in France that we all know, and he's now working in Meta since 2017? 19, yeah. So he was hired for the COVID age, right? Yeah. And actually, I knew about his name because of the joint works he has written, in particular with Amaury Ayat, that was delivering a lecture in this series a couple of years ago. And it was precisely in the presentation of Amaury Ayat that he was lecturing on, in particular, how to use artificial intelligence and machine learning ideas to tackle some of the classical problems in dynamical systems and in control dynamical systems, as for instance, computing Lyapunov functions and discovering new Lyapunov functions. And well, I thought after Amaury's lecture that we should have a second one by François with his own point of view, much closer to, I think, to say technological transfer and innovation. So thank you again, François, for your visit. And the stage is yours. Thank you.
Okay, hi. So yes, I'm François Charton. I work in Meta and also in École des Ponts in Cermix with Amaury Ayat. And in Meta, I work in FAIR, which is a research laboratory that depends of Meta. So we're one of the few people inside Meta that are sort of allowed to do some kind of blue sky research, etc. I'm on the blue skyest part of the lab, which is not always easy, but yeah. And so my subject is AI for mathematics. So how do you use AI to do mathematics? And I will talk about two things. Using AI to do mathematical discovery. I'm not interested in doing all math. I want to do new math. I want to do discovery with AI. And using math for AI, you know, what math can help you learn about how AI model learn and maybe improve AI models. Je peux me le mettre autour du cou?
Non, attends, tu fais ça d'abord. Voilà, et maintenant, voilà.
Oh, c'est génial.
Et comme ça, tu serras les mains.
C'est génial ce truc. Ça marche? Okay. So, very quickly, a few words about architecture. So, I'm working on a model which is, you know, the standard model in AI these days, which are the transformers. This is what powers ChatGPT and all the large language model that you know. It's originally, and this is important, an architecture that was meant for translation, from automatic translation from one language into the next. And it was introduced in 2017 with this in mind, with translation in mind. And a transformer, at least the kind of transformer I use, are made of two parts. You've got an encoder that processes one language, and you got a decoder that processes the other language, so the source language and the target language. So the role of the encoder is to transform your sentence, here in French, sous le pont Mirabeau, into first a set of vectors in high-dimensional space, so mathematical stuff. Then it will be processed by many layers of an encoder into a mathematical representation that is a sequence of numbers, of 4 numbers in this case, in high dimension, 4 vectors in high dimension. And the decoder will do the English or German or Chinese part. And the way it does it is that it translates, it spits the word one at a time. So basically here we are in the situation where the 2 first words under the have been processed. And you're going to feed the transformer, the decoder, with what you have decoded so far. And also the representation produced by the encoder, so the internal representation of the input. And it's going to spit the next token, which is Mirabeau, which you might notice is interesting because in French, the third word is bridge, but the transformer knows that in English you have to change the thing. So that's the way basically it works. And these encoder and decoder are made of many layers, tens of layers in ChatGPT and stuff like that. And a transformer layer it's a little complicated. It's more complicated than your typical layer from a neural net that you know. So the way it functions, you know, you have input vectors, the I1 to I4. that are connected to the output vector with what is called the residual connection, so they're just copied, and then you add stuff to it. And you had two kinds of stuff. You had attention, which is something that takes care of the correlation between the different words in the sentence, so between the different vectors. So you could think of it as decorrelating the different elements, just as you would process a time series and eliminate, seasonality, monthly seasonality, or something like that. And then the second part, the FFN, feed-forward network, is a regular three-layer neural net, as everybody has been using since the 80s or something like that. So the transformer layer is a fairly complicated thing, and you stack several layers in order to train and to learn to translate. So how do you train such machine? It's called supervised learning. This is the only thing I will discuss here. So you start with a model, and the model is initially randomly initialized. So basically, it's a big set of parameters, tens of millions, sometimes billions of parameters, which are random. And you push examples through this machine. So you got pairs of examples, X, Y. X is the first language, Y is the translation. And so you push X into the model. The model is going to predict, in the beginning, something totally crazy because the model is random. So how does it doesn't know how to translate at all. And you're going to compare the prediction of the model, so the translation your model predicts, M of X, with Y, the correct or one correct translation. In the case of translation, there's not only one, but one correct translation. And you're going to calculate an error by using what is called a loss function, which is a differentiable function. It could be pretty much anything. In those cases, we use something called cross entropy. You can think of it as a glorified Hamming distance. It's pretty much that. But yeah, and since the loss function is differentiable, you could calculate the gradient of the loss function, and you could calculate it with respect of all those millions of parameters in the model. And you can do that automatically. This is how it works. And so you have the prediction, you have one value of X. You've got the loss with the prediction and Y. You know which weights were wrong, and you can nudge the model in the correct direction. So move a little the weights of the model so that if it's another time the same example, it would make a little less error according to the loss function. Okay? And the idea is that you're going to rinse and repeat this on millions of examples, tens of millions of examples, trillions in the case of ChatGPT. And the magic of it is that it might work. And actually, it often works. And of course, so you're going to train, you push examples, question and answer, the model calculates a loss. The loss is differentiated, that changes the weights of the model, and so on. Okay? And of course, every n example, once in a while, you take a set of test data, so data you haven't seen during training, examples, and you calculate. And you just say how many good predictions. So you can follow the accuracy of the model, whether they progress or not. At this point, I'd like to introduce just one small concept. We distinguish between two kinds of test data. The in-domain tests, basically held out example from the training set. So examples that have the exact same distribution as the training data. But we'll talk a lot about out-of-distribution data. So this notion of distribution of data is not very well defined, but I think you can understand what I'm saying here. Basically, in many cases, the distribution, what you want to predict is not necessarily distributed as your training data. And sometimes you're going to test on examples that are slightly different from the training data. So for instance, you would train from BBC English, but you would like to test it on more colloquial, like slang English or something like that, and see if it works, to know whether the model generalizes far away from its training data. So the question I'm interested in is whether you could use this to do mathematics. So if I can learn to translate a German sentence into English, just from example, could I learn to translate a mathematical problem, a sentence, in some language, into its solution? Just saying the solution is a translation of the problem. So in other words, suppose I have the sentence 5 plus 7, 3 words. Can I translate it or train a model to translate it into 12? Could be one word, 12, or 2 words, 1, 2, if you want to go for the digits. This is up to you. There's a lot of freedom there. If I have that 6-word thing, which is x squared minus x minus 1, which is a polynomial, but the model doesn't know it's a polynomial, it's just a sentence, right? could I translate it into the roots of the polynomial or any other interesting quantity about this polynomial? Could I translate, an expression like cos 2x into its developed version as a polynomial in cos x? So there are reasons why this might work. The first thing is that once you went over, the surprise, considering mathematics as language and solving problems as translation is relatively natural. It's not really difficult to think of mathematics as sentences and sequences. Numbers, they're just sequences of digits. And mathematical objects like matrices or vectors are just sequences of numbers, so sequences of digits. And functions, we'll see, a function you can represent very easily as a tree, abstract syntax trees in computer science, for instance, and a tree can be enumerated as a sequence. So it's very easy to represent everything as sequence, so it's transformer-friendly, if you like, much more than an image, say. And also, we know that we need lots of examples, but in mathematics, you can generate examples. This is the good thing with mathematics. You can have programs that generate problems and solutions. Besides, initial experiments seem to work. So I'm quoting ancient work. In 2019, actually, with Guillaume Lampe, one of the founders of Mistral, we actually showed, that was the very first work on the subject, that you could train a transformer to calculate a symbolic integral. So you give it a function and it calculates the integral of the function. And it does it as well, we say better, but let's say as well as Mathematica or Wolfram Alpha, the best computer algebra we had at the moment. So, that came as a surprise, but it does work. 2 years later, I had worked on linear algebra, and I showed, if you represent matrices, just as I said, sequences of numbers, which are sequences of digits, I can use a transformer to calculate eigenvalues and eigenvectors. And this, again, is surprising because it's not basic arithmetic, but it works. You get very good accuracy with that. Of course, there are also many reasons to doubt that this could ever work. So the first thing is that this idea of learning math from examples is absolutely unnatural. We don't learn math from examples. We learn math from rules. And we learn to assemble, to compose rules. And it's known that transformers are obscenely bad at compositionality. So it's learning math in a way that is very non-math-like or non-human math-like. So this is strange. Another problem is that the transformer learns from examples and examples of problems of solutions. So the transformer learns from problems we know how to solve. But of course, the goal of this is not to solve problems we know how to solve. That would be to discover new mathematics. This is the goal. So how can you learn new mathematics by training only on things, on all mathematics, on things you know how to solve? Is AI-based discovery even possible? So I'm going to show two examples from last year that suggest that, yes, AI discovery is actually possible. So the first one is, it's our last installment on Lyapunov function, maybe not the very last, but close to the very last. That's a paper from last year with Alberto Alfarano and Amaury Ayad from CERMIX. So Lyapunov function, we start from dynamical systems. So dynamical system, it's a system of n equation in n variable with x dot, dx on dt equal f of x, where x is a vector. If we have an equilibrium, so it defines the gradient at every point. And if you have an equilibrium, at an equilibrium x0, usually I will consider x0 to be the origin, we must have f of x0 equals 0. The gradient must be flat at the origin, obviously. And then we have a couple of theorems, spectral mapping theorem, that shows that you have a local minimum if all complex eigenvalues of the Jacobian at this point have negative real part. So, yeah. This is something we know how to do. This is a very local property. And actually, in 2020, with Guillaume and Amaury, we showed that transformer can actually learn to find the eigenvalues and all that. So this can be done. But here I'm interested in something more difficult and slightly wilder. The question is global stability. So the question is, say, suppose you have a stable equilibrium at the origin. Can I guarantee that if I start not too far from this equilibrium, I will never drift to infinity. I will always stay in a bounded circle around, in a bounded sphere around this equilibrium. So if I start in the blue circle, will I always stay in the red circle? Okay, and this is a much harder problem because it's a global property of the system as opposed to a very local property at the equilibrium. If this reminds you of, the stability of the solar system, the n-body problem, Laplace, Poincaré, the King of Sweden, Netflix even, yes, you're right. This is not exactly it, but this is pretty much the same story. So actually for Lyapunov function, for this problem, we have a solution that was discovered by Lyapunov in 1892. And this is a very old open problem. So Lyapunov says that if you can find a function v that is C1, so continuous with continuous derivative, such that it has a strict minimum at the optimum, so 0 here by convention, it's infinite at infinity, and it verifies this strange condition, the gradient of v dot the function f that defines the system is always negative. I say it points away from, don't know if it's the right image. Then the system is guaranteed to be globally stable. This is only a sufficient condition, but throughout the 20th century, it has been shown that for very, very large classes of systems, it's also necessary. So it's sufficient, but pretty tight. So Lyapunov theorem is magical because it says that, if you can exhibit a function that has these properties, then you've guaranteed that your system is stable no matter where you start. And this is pretty spectacular. So give you an example. This is a very simple system. You see two variables. Our model actually finds this big sum of square function, and you can prove that the three conditions are verified. And so this system is globally stable. But this looks good, but the problem is that there is no general method for constructing Lyapunov function. And it's not for lack of trying. Lots of people have been trying to find ways to construct those functions, and there is no method. No one has been found, except in very specific case. So if you have polynomial system, small polynomial system, so few variables and a low degree, and if they have a sum of square Lyapunov function, then you have computational method that will find them. Those are known as source tools. There are tools that do this. So this is an example of those. But it's been shown recently in 2011 by Amadi that actually polynomial systems don't always have sum of square Lyapunov function. So it only addresses a small set of systems, and it doesn't even address all the stable polynomial systems. Okay, so the thing is, could we train a transformer, feed it a system, and have it predict a Lyapunov function? Could we train it from examples, give lots of examples, and have a system guess a Lyapunov function for us? So how do you represent that in a transformer? Well, a function can be represented as a tree. You see here the kind of trees you get. And when you have a tree, you can always enumerate the tree. There are many ways. This one is prefix enumeration. It's not really important. And it's easy to represent, the system as two functions and the output as one function. And so it's easy to put that into the transformer. And then when the transformer predicts a function, you need a verifier to check whether it comes with no guarantee. So you need a way to verify. But you can always verify the prediction of the transformer by using the free condition and using a solver, SMT solvers or tools, these kind of tools. The difficulty here is how am I going to train this? Because, I need tons of examples. So in a perfect world, I need pairs of systems and Lyapunov function. So in a perfect world, what would happen? I would randomly sample a stable system S. I would compute its Lyapunov function and add the pair S and V to the training set and repeat until I have 1 million or 2 million examples and train my model on that. And this can be done for my small polynomial system because it takes a lot of compute, but you can do it. But in reality, it doesn't work. And this is the whole problem with trying to solve an open problem. You don't know how to solve an open problem or it wouldn't be open. So it doesn't work because, just sampling stable system, the only way to know that the system is stable is to have a Lyapunov function. And this is what we need, not what we have. So we don't even know if a system is stable. And finding a Lyapunov function, well, that's the exercise. So we don't know how to calculate them. So, generating this way, in French we say quand les poules auront des dents, when hens will have teeth. So it's never going to happen this way. So The classical method for generating data to train the model doesn't work here because the problem is open. So how do we do it? We follow what we call the backward generation method. So the idea is that instead of finding the solution of the problem, you're trying to find the problem of a solution. What am I saying here? I'm going to sample a random function v, which will be C1, have a strict minimum in 0, and be infinite at infinity. This is much easier, right? So that's my Lyapunov function. And then, from this Lyapunov function, I want to find a system f verifying the third Lyapunov condition. So I'm going to generate solutions and discover problems to do that. So this is the method we're going to use, but it comes with problem. You know, it's not as nice as the FAUMoD method. There are two caveats. The first thing is that you want V and F to be as generic as possible. You don't want an obvious or a degenerate solution to the problem of finding V and F, because the model will not learn, you know, the general case, but just a special case of Lyapunov functions. Okay, so you want to sample V from the largest possible class of continuous function with a strict minimum, etc. And for a given V, F must be sampled as randomly as possible from the whole class of the function, verifying the gradient V dot F negative. Okay? And even if I can do that, you must understand that the distribution of the data will not be the distribution of the test set. You know, my training data will be very biased because of the generative method. There's absolutely no reason that generating problems from solution results in a correct, whatever correct mean, distribution of problem. So I will be sort of out of distribution all the time. Also, when you do that, there is another caveat, is that you have a method for calculating the system from the Lyapunov function. You want the problem to learn to calculate Lyapunov function, not invert the generative method. If you start with a naive generative method, then chances are that the model will just learn to reverse your method, and you will not learn nothing, or you'll not solve the problem. To give you a very silly example, suppose you want to calculate the roots of polynomials. It's very easy to calculate polynomials from their roots. You know, you got 3 roots, and you calculate x minus this. Of course, if you submit to the model p of x equal x minus 2, x minus 5, x minus 7, I said it's a trivial example, the model is not going to calculate the roots. It's going to read them from the input, and this is not what you want. If you develop it, you're fine. If you develop it, the problem becomes complicated. You have the same kind of problem, just more vicious, in the case of Lyapunov functions. Okay, so how do you generate the Lyapunov function? Well, you want to V infinite and infinity with a strict minimum in 0. The hard part is the strict minimum. It's a hard problem to find, you know, to sample the function with a strict minimum. So the way we do it is that we sample the function, which is the sum of a simple function with a minimum, and a function that is unbounded at 0, non-negative unbounded around 0 with a minimum at 0. And this would be enough. So there are tricks for that. I'll spare you the details, but there's a complex procedure you can find in the paper. How do you find so suppose now you have a V you're happy with. How do you find F? So you want to have a gradient of V dot F negative. You see there's an obvious solution. You could decide that F of X is minus gradient of V. You know, you would have the minus the square of the gradient, and this is always negative. But of course, this would be a ridiculous solution, because if you do that, you're no longer finding V from F. You're finding V from minus nabla V, minus the gradient. So it's not a Lyapunov problem you're solving, it's an integration problem. You want to find the integral of F. So it's an easier problem, or at least it's not the same problem. So you can modify that. So first you could multiply, you know, the coordinates of nabla V by random positive function. If you multiply them, you're changing the scales in all directions. Your dot product is still always negative, but there's no way you can solve, you know, reverse this process by integration because you have random parts. You can do even better by adding to these values a vector, you know, an element from the hyperplane v dot nabla v equals 0, so an element where everything is 0. And when you do that, you have the most general possible sampling of F verifying the third Lyapunov condition. So all this, I don't go into the details, but all this to say that the real hard part is generating your training data. You have to be very prudent. You have to check. It's very difficult to do. But anyway, we ended up with training sets. So we generated 2 backward data sets. So a data set of polynomial system with 2 to 5 equations generated, with the backward method, 1 million of them, and a non-polynomial set. So actually, it's not fully non-polynomial. They're polynomials of different functions, like trig polynomials or polynomials with exponentials and trigs and stuff like that. But practically, and those latter things, we have no methods for calculating the Lyapunov function. So this is totally non-Lyapunov, open territory here. And then we use source tools and a lot of compute to generate 2 polynomial forward sets. So FLYAP, it's very expensive, so you can only generate 100,000 in several weeks on many thousand CPUs. So this is very, very costly. So we could do that, and we have another sample, F-bar, which is a larger sample, but solve a related but slightly different problem, the notion of barrier function. I won't get into the details, so keep in mind that we have 2 backward data set of 1 million data, and 2 forward data set, one really of Lyapunov function and another one on a related problem, but related but close. So what's the performance? We train the model. What result do we see? So the first thing we want to do is look at in-domain performance. So for every data set, we generated, say, 1 million examples. We kept 10,000 for test that weren't seen during training, and we estimate the model once it's trained on the 10,000 the model has never seen. And you can see the results are quite impressive. So BS means batch size is the number of guesses the model can do. So, in the most basic version, the model has only 1 guess. But it's not more costly for the model to have 50 guesses as a Lyapunov function. And of course, you'll improve the results. So 1 guess or 50 guesses. You can see on the backward data sets, on the polynomial, you get almost 100%. So everything is predicted perfectly. And on non-polynomial, with batch size 50, you get to almost 90%. So that's pretty good. Same goes with the forward data set. But this is a bit too good to be true. The problem is that suppose my model has learned to invert the generative procedure. What would I see? Exactly this. So this doesn't prove that the model is not cheating. The model could be cheating and could have learned, at least in the backward case, just could have figured out how I generated my data. So the way you can test that this really works is to be out of distribution. So basically, you're going to train your model on the backward data and test it on the forward data, which was generated in a different way. So even if you manage to invert the generative procedure, this is not going to help you at test time because the test example doesn't come from the same set, right? So out of distribution performance, what you can see here is that the backward data set, when trained on FLYAP, so when tested on the forward data set, achieve about 75%. Okay? Interestingly, the non-polynomial data set works better than the polynomial data set, even though the test set is polynomial. So it's not always completely intuitive. It might be equivalent, this said. They work much less well on the comparable, on the related problem. That's normal. It's a different problem, so you expect a loss. And you can see that it does totally badly for the forward data set. So my forward data set, the training set was quite small, doesn't generalize to the backward. But the backward generated data somewhat generalized to the forward data, which means that the model cannot cheat. The model cannot cheat because if the model somehow managed to invert the generative procedure, it would fail on the forward data set, right? But there is a cost. You see we're not at 90%, we're only at 75%. And the cost is due to the fact that the backward and the forward polynomials have a different distribution. So the kind of example you see in the test set are very different from the kind of example you see in the train set because they were generated in very different ways. So they cover different parts of the space of systems and their Lyapunov functions. So at this point, the question is, so that's already a pretty good result. The question is, could we improve it? So in order to improve it, we use a technique that we introduced with Sami Jelassi 2 years ago that is called priming. Priming is a way to improve the functioning of a model when it has to generalize to a different distribution than the one it was trained on. So suppose you train a model to do addition, and the model is trained to add number with 10 digits. And then you want to test the model on numbers with 12 digits or 8 digits, not 10. You will see a drop in performance up to almost 0. That's the length generalization problem, because the model hasn't seen an 8-digit on a 12-digit model, and it doesn't know. But what priming noticed is that in order to cure that, you don't need to retrain the model. You just need to add a tiny number of examples with the right length. So the problem is that the model never seen an 8-digit or a 12-digit case, but just give them 10 of them, and the model will manage. You don't need millions of examples in this case. So we thought, okay, here we could use that. We have this out-of-distribution problem because the backward data is different from the forward data. But let's keep 100 forward data and mix them into our backward data. What happens? And you can see here, if you had 300 or 100 in FLIAP, 100 forward-generated data, your performance jumps from 73 to 82%. So you can get up to a 10% or more than 10% increase in accuracy just by using these tricks. You need to have a few examples that you can solve. And this is cool because in many open mathematical problems, there are easy cases that you already know how to solve. So this is a situation that is very standard in mathematical discovery. You just add a few of the cases you can do to the training set. 100 is enough or 500 is enough, and it will change your performance. The funniest part is when you add data from the related problem, F-bar. Because when you add F-bar, you can see that not only does the performance on Lyapunov increase, but also the performance on the related problem increase. So you can, if you like, kill two birds with one stone in that, because you add examples that are better distributed with respect to your test distribution and also pertain to a different problem or related problem, you improve both the accuracies, the accuracy on the Lyapunov problem and the accuracy on the other task. Okay, so we can compare. So there were previous attempts to do that, existing AI model to do that. So to be fair, they're slightly different. These AI models that wanted to calculate Lyapunov function were doing it in the case of robotics, where you guarantee that the changes, the distance you are from the equilibrium is very small, or very small in most dimensions. So, but you can see we clearly beat all the state of the art. It's really a game changer compared to what AI or other methods can do. So there comes the question, have we really solved an open problem? So I did show that model trained on backward dataset can generalize to generic polynomial system that SOS can solve. I did show that priming is going to improve performance and allow generalization to related tasks, the barrier-Lyapunov function. I did show that we are better than AI methods, but we are still solving the polynomial system that we know how to solve because we have source tools. So again, as the French said, tout ça pour ça, all this for this. The real litmus test is different. So last part of the paper, we said we go into the wild. So into the wild is, you remember, I cannot know that the system is stable unless I have Lyapunov function, which is what I want to solve. So let's act differently. Let's generate random data set, which we don't know whether they are stable or not, and see what gives, what the model produces. We don't know how many of them, so we don't know what 100% mean. We don't know what is the value, but we can see if the model can discover those random data. So we generated 3 data sets of random systems, poly3, so polynomials with up to 3, degree up to 3, degree up to 5, and non-polynomial systems, 60,000 and 20,000 examples. So you can see the original methods, those tools, AI methods, they are not very good, but it's difficult to judge them. We don't know how many systems are stable. But you see that our system is able to predict about 10%, up to 12% of those systems. And for the last line, these are things where we have 0 method. These are all things that we cannot do with existent methods. So you see that our models, if you put it on purely random system, we don't know whether they're stable or not, it managed to find 12% in 12% of the case, a Lyapunov assumption, therefore demonstrating that the system is stable and proving it with a Lyapunov function. We don't know what is the limit. You know, maybe 60% of those guys, I doubt it, are stable. Maybe 20, maybe 13, I don't know. But it seems to work. And there's room for improvement. The fun thing is that, you know, just as we did priming, we could improve it by, when a model gets correctly a Lyapunov function, we could feed it into the training set and fine-tune the model on that. So we could improve just by adding more of the things we've done. So we tried it just for the fun of it and managed to get from 12% to 13%. So possibly we could use many things. And the funny thing is that this is exactly what people are doing, you know, when they do reasoning in large language model, the DPO, GRPO, all those things. This is exactly that. So the good thing here is that these elements would be open to, we could reuse a lot of things that were invented by other teams not doing AI for math. So you see, we can provide solution to an open problem in this case. So yes, you can do discovery in this very specific case. It takes a lot of work, especially on generating the data. You need a mathematician around you. It's not, you know, it doesn't come for free with your ChatGPT package. Right now, we're able to find Lyapunov function of random system. The real test would be to go for interesting system, whatever this means, but systems people, yeah, find an interest in solving. The hard part is data generation, and you must test your model out of distribution if you want to prove that the model is not cheating. The litmus test, the real test, is the in the wild test where you have random data, but then you don't have the value of the benchmark. You don't know what's the best value you can achieve. And finally, there's a lot of additional methods, so there's a lot of room for improvement. Okay? So let me go to the next thing I wanted to show you in terms of discovery. It's a totally different paper written last year with Jordan Ellenberg, Adam Wagner, and Jordi Williamson, called Pattern Boost, and it's about using generative AI for combinatorics. So I'm interested here in extremal problems in combinatorics. You know, you want to find the largest object in a class. So for instance, you want the largest graph with n vertices, largest number of edges, such that there is no 4 cycle. This is a fairly famous problem in combinatorics. Or you would like, the third one is an Erdős problem. You have an n cross n grid, so a hypercube, and you want to find as many points on this cube so that no 5 points lie on a sphere or a plane. You know, 4 points always lie on a sphere, but 5 is less random. It turns out there are very, very few in this case. So these are problems that are studied, but we have very, very few methods except enumeration. So the thing is that could we use AI to find competitive solution? We don't speak of best solutions here. Could we use AI to help us find good solution or better solution than what we would discover in less time than what we would need? And this was greatly inspired by a paper by Adam Wagner from 2021 about disproving a conjecture in graph. Adam is a graph theorist. And he wanted to use reinforcement learning, so not transformer, this guy, to find a counterexample to a conjecture from Aouchiche and Hansen, which dated from 10 years before or something, which basically say if you have a connected graph with a certain diameter is the largest distance between two nodes, and a certain proximity. Proximity is the average distance between nodes, and then you have got the distribution of the spectral values, so the eigenvalues of the adjacency matrix. Those three things are sort of related by a relation. It seems logical that there should be a relation, and the conjecture was that. And so Adam trained his model to try to find a conjecture, and he couldn't find a counterexample. What he found was that nice graph that you have at the top. You know this nice flower with a lot of petals, and you got two long stems. And this is not it doesn't falsify it's not a counterexample, it doesn't falsify the thing. But a trained mathematician could look at that and say, aha, I got the counterexample. And Adam modified it in this. So you see, you just got longer stems, and way more petals. And this is a counterexample. So the idea here was that in those, there's a lot of mathematics to be proven when you have a conjecture. You could find a counterexample just by having the model generate for you something close, something tight enough, And then, in many cases, the mathematician could save it or could transform it into a proof, something valid. Okay? So pattern boost works exactly this way. It says, the intuition is that if you have a given problem, the good solution, the solutions you want, all have an air of family. You know, they share a number of features. Your graph will be sort of empty in the middle, or it will be very connected or very unconnected, but it will have one connected component or something like that. So the idea is that those features of good solution could perhaps be learned by a model, by imitation. So you could train a model to predict or to generate by predicting the next token, just GPT-like, the next token of the good solutions, okay? And use this model to generate more good solution. And what if you keep the best of the good solution and put them back into the model and fine-tune the model on that? Are you able to bootstrap yourself and improve? So there is a theory that you might have read in the newspapers, because it's newspaper material, which is called model collapse, which says this doesn't work. And I was in 2 papers on model collapse, so I must plead guilty of this. The thing is that it says, oh no, if you train a model on its own data, the model is going to collapse. Actually, what we see here is that with a little improvement, basically, if you eliminate all the incorrect solution generated by the model and improve them somewhat, this works. So, you know, this led me to not to believe in model collapse. But practically, you see how pattern boost works. It works a bit like a genetic algorithm. I explain that in a minute. You randomly generate a population of candidates. So you generate 1 million or 10 million examples, 10 million possible solutions. You sort them and keep the 1 million best and train a transformer with it, okay? Once the transformer is trained, you generate 10 million more. You improve them locally, so you eliminate the wrong solutions. The model doesn't guarantee that the solutions are correct. And maybe the correct solution, you could improve them with a local solution, something easy in order to make them a little better. And you keep the best and fine-tune the model on that. The method used, we used an open source code from Carpathy 2023, which is an implementation of GPT-2, so something very, very easy to do. And if you think of it, it's a lot like a genetic algorithm. You know, in a genetic algorithm, you have a population of solution, and you transform this population through crossover and mutation into a better population. Here you have a population, you train a transformer with a population, or you fine-tune a transformer, and you use the transformer to generate a new population. So the genetic operator is your transformer here. Okay, so we're interested here in the no-square problem. So you want to construct the largest graph with n vertices without cycles of 4. It's a well-studied problem. I mean, good combinatorists, Timothy Gauss, people like that, have worked on it and found solution. We know exactly the number of solutions up to n equals 40. We have guesses until 50, and after 50, nobody knows. Pattern boost isn't the best tool to use this, but it's competitive. I mean, we managed to solve problem up to n equals 33, so it's not bad, at least. It surprised the combinatorists around the table, say. So how does it work? So this is what happened on the left. You can see what you get if you have a classic local search. So you're going to generate random solution and you improve them locally. And then you look at what you have after 50 million tries. And you can see this is the distribution of score. The score here is the number of edges. It's what you want to maximize. And you can see you have a unimodal distribution with a mode and an average at 81. And the best you could find was 86. If you use pattern boost, you see that your distribution has the same characteristic but becomes bimodal. Because of the training of the best solution that you re-input to train the model tends to generate more good solution than you would have with a random approach. So you have an improvement. You still have a big diversity set of data that are just average, but you gradually build a better data set of better solution. Okay? And here are 20 examples running. So you could say, oh yeah, but this is luck. This is random search. You know, you might be lucky on that. So here are 20 different models run from many generations. It takes a lot of time, so it's not efficient at all. What you can see on the left is the number of edges you have on average on the best 10,000 solution at every generation. So you can see that it goes up slowly, because of the discrete value of the outcome, it has this strange shape. But everything goes up, but some models are better than others. And what's interesting is if you see on the right, this is the best solution. You can see that the very best model, the light blue model, found the best solution, 96, but it found the second best, 94, and it was the first one to find the next best, 93. So it's not as if it's a glorified random search. The models that perform are certain models. So certain models do learn something that allow them to outperform the others. We don't know what, but this is, yeah. Okay, you can improve things with that. So pattern boost, so in the end, we used it to provide a counterexample to a fairly old conjecture in graph theory, a Graham conjecture. We also discover on the Erdős problem of the hypercube a very small dimension. For small dimension, people thought they knew the correct solution, and we proved them wrong. We discovered a small solution that nobody had seen before. So it sort of works. It can be state-of-the-art on some problem. It's sometimes even better than that. Sometimes it's just competitive. But we think it's the kind of thing that works. And compared with approach like Lyapunov, where you really needed to have Amaury Hayat or someone like that around you to tell you all the details, this sort of works out of the box. Every time you have maximization, you can probably use that. Okay, so these were my AI for math. I'm going to rush you about math for AI and won't talk about half of what I wanted to talk about because I have no time. So this second part is about, how can you use math to try to better understand how the models work. So I'm going to walk you through a paper from 2024 about the greatest common divisor. So the idea is, suppose I have two numbers. I randomly sample two numbers between 1 and 1,000,000. Those are two pairs. I can encode them as sequences of digits in some base, B. I'll try many different base. And I want to predict their GCD. Okay, the greatest common divisor of those. So I will encode my numbers. I will predict the GCD. It has to be known that, the GCDs are, the law of the GCD, the probability that a GCD is equal to K is proportional to 1 on K squared. So there are 4 times more GCD1 than GCD2, 100 times more 1 than 10. So the values are usually small. It's more a classification problem than anything else. And so the idea is that I'm providing two sequences of digits, A and B, and I want to predict the value of the GCD at the end. Does it work? So I'm going to compare the importance of choosing B, the base, the encoding base. So how do you choose the base? So you could think that if you have a small base has a very small vocabulary, which is easy to learn. Base 2, it's only zeros and ones. Base 1,000, you got 1,000 words, different words, digits to learn. But you have very long sequences that are a little more complicated to tackle. Okay? Also, if you have a composite base, in composite base, it's easier to learn divisibility. In base 10, divisibility by 2, 5, 10, 20 is very easy to judge. You just look at the last tokens, last digits. In base 7, divisibility by 2 is difficult to judge. Okay? So, can you learn the greatest common divisor? This is an important problem because it has been shown that transformers sort of suck at arithmetic. They're very bad at multiplication, for instance. So could you learn GCD if you can't learn multiplication? So the first try was a very, very small transformer, and I use a composite base 30, 2 times 3 times 5, so divisibility is easy to figure. And I train my model, and you can see that after only 300,000 examples, the model predicts 85% of all the GCDs in my test set that it hadn't seen at training. And if I insist a bit, I end up at 95% or something like that. So it looks like GCD are easy to predict, right? Well, until you try base 31. Base 31, you start at 61, and it stays at 61. And the 61 is obtained because the model always predicts the most common GCD, which is 1. So the model in that case only predicts 1 and nothing more. And it's worse if you go on, because from top to bottom, you got base 30 and 6 and 10 and 12 and 2 and 3 and 31. and the performance depends on the base, and the GCD should not depend on the base. So obviously something very wrong is happening. It looks like it works, but it doesn't. So what happens? So for this, we could look at what the model predicts, for instance, in base 2. So here, I train my model, and then I have a huge test set of 100,000 examples, with 1,000 examples with GCD1, 1,000 examples with GCD2, with GCD3, etc. And for every value of the GCD, I'm looking at the model most common prediction, how common it is, and what it is. Okay, and you can see that the percentage, which is how common it is, the model makes only one prediction, no matter the GCD. So if you have two pairs with GCDK, the model always predicts the same, right? But what's interesting, the correct prediction in red are 1, 2, 4, 8, 16, 32. I think you can spot the pattern. The powers of 2 are correctly predicted. But it's more interesting even, you see all the odd numbers are predicted as 1. And the even number are predicted as the largest power of 2 that divides the GCD. So what is my model doing? Well, the model counts zeros. The model is just looking at the binary representation of the number. And you know, if both numbers end by 1, then you predict 1, right? Because GCD must be 1. If it ends by 2 zeros, 3 zeros, etc., you count the zeros and you take the min. And you answer 2 to this value. So this is exactly what the model is doing. Sometimes it works. You can see that GCD of 52 and 68 will be correctly calculated. And of course, the GCD of 12 and 24 will not be correctly calculated. But that explains what the model does. And the same happens in base 10, etc. In fact, when you look at the GCD, there are 3 rules. It says that first, the predictions are deterministic. The model, if you have a pair with GCD k, the model predicts a certain function f of k, so all the pairs with the same GCDs are predicted the same. And this is spectacular because we humans cannot do that. If I give you 2 pairs of numbers with the same GCD and say, same, not same, you know, you need to calculate, you need Euclid, you need something to do it. It wouldn't work, you know, this way, but the model can do that. Second thing is that the correct predictions are products of primes dividing the base. And this explains the difference by the base, right? And finally, the predicted value can be explained, you know, it's just the largest correct prediction that divides the GCD. So the model is clearly cheating here, and you can see that the values, you know, you got performance for a lot of different base, and below you've got the number of GCDs it actually correctly predicts, and the number is very, very low among the first 100. So the model doesn't predict many GCDs, just cheats, and it depends on the base. But there's a surprise. In base 1000, normally my model should predict as well as base 10, 13 GCDs, but it predicts 22. So something different is happening here. And for large base, we notice that, you know, after 25 million examples in base 1000, the model predicts, as advertised, 12 GCD. But if I wait for a very, very, very long time, the model starts predicting way more GCDs, and it changes all at once, because the model starts predicting GCD that are multiple of 3, and 3 doesn't divide 1000. So the model, if you give it enough time, will end up learning divisibility not by the base. It just needs a lot of time. And this generalized, this is base 2023. This was, the paper was written in that year, which is 7 times 17 square. So we expect that the model will be able to predict, you know, GCD1, GCD7, GCD17. And actually, this is what happens in the beginning, you see. But then if you wait for a very, very long time, I have 3 models here, it happens at different time, all at once, the model learns divisibility by 3. And so instead of just predicting 1, 7, and 17s, it predicts also 3, 1 times 3, 21, 7 times 3, and 51, 17 times 3. So at one moment, suddenly, the model splits and learns a new divisor and learns a bunch of GCD this way. The same happened later with divisibility by 2, and then divisibility by 4, etc., etc. So what's proven here is that, or what's seen here, is that if you have a large enough base, the model starts by learning the divisors of the base, but it doesn't stop there. It's going to, you know, improve at some point. Okay, so altogether, what have we learned? We learned that the GCD can be learned, and that the model is learning a very specific algorithm, which is more like a sieve algorithm. It's clearly not Euclid. It's a sieve algorithm in the sense that you learn the divisibility by first the divisors of the base and then more or less in order the small primes and powers of primes at 2, 3, 4, 5, etc., etc. And so if this continues, if you have enough example and this continues to infinity, at some point the GCD all GCD will be calculated. You know, once you have all the divisors of your GCD, you will be good. Of course, it's totally inefficient, but the model learns an algorithm that works. Okay. The thing is that it's insufficient. It's a very slow thing. So the question is, could we accelerate it? Can I take a few more minutes? Show that? Yeah. So at this point, I'm only going to look at base 1000. So you remember when base 1000, I was able to predict 13 GCD out of the first 100, maybe 22 with the grokking, you know, the things that happen. Can I do better? So there are 3 strategies that we discovered that could help. The first one is very surprising. It's about repeated examples. The second one is about the distribution of operands and outcomes. So I'm going to cheat on the training data and use the changes in the training data to improve my results. So repeated example, it was a paper from last year. Same problem here, GCD. So the idea is, you know, suppose you generate your training data. You can generate as much as you want. Would you prefer to have a very, very large training sample of single-use example or a smaller sample of examples you repeat? Intuitively, you would like the first, right? More diversity, more example. But this is wrong. What we noticed is that if you have a smaller data set, your model will learn better. So this is a GCD example. Well, the different colors correspond to the size of the training set, okay? And the x-axis is the number of training examples, so the number of repetitions somehow that the model has seen, so how long you train. So you see, if you train for 30 million examples, you can see that most of the model only predict 13 GCD, as advertised before. But the 2 models with the smallest training set, 1 million and 5 million, that have been repeated 30 times or 5 times, predict 20 GCD, much better. And if I go further, you know, if I go to 60 million example, you can see that, okay, the 1 million, you don't have enough. So at one point it stops. But you can see that the best model is the model trained on 25 million example that can predict 55, almost 60 GCD, which is way more than we ever saw. You know, so now it can predict very, very well because we have only 25 million examples. If I had infinite data, so single-use example, I'll still be only at 23. And this goes on if you go to 1 billion examples, so that's really a lot of training. You can see that the best model are the model trained on 25 or 50 million examples, repeated many, many times, whereas the single-use data is only at 25. Okay? So a first way to improve this is just use repeated example, use a smaller training set, and repeat the example. I don't know why this happened, but I've seen it happening in different cases. So this is really something that works, and you can improve the GCD this way. A second way to improve is the distribution of operands. You know, if you generate A and B, the 2 operands in the GCD randomly, most of the time, the numbers will be large. So the model is going to learn the GCD from large examples. This is not how we teach students, how we learn ourselves. We learn from small example and generalize to large one. So what if? So instead of distributing the data uniformly, we now take a log uniform distribution. So basically, we say there are as many, in the training set, we have as many operands with 1 digit, as 2 digits, as 3 digits, as 4 digits, as 5 digits, etc. So the probability of operand k appearing is proportional to 1 on k. And if you do that, you can see that your models are going to improve greatly. So you see for different base. So it will be a little more noisy because of the distribution, because the distribution has too many small numbers. But you can see that the distribution, the GCD you achieve, so for base 1000, you go from 22 GCDs predicted to 71. So you're getting very close, right? Another way to do that, so we change the distribution of outcomes, operands, we could change the distribution of outcomes. You remember that the small GCDs happen much more often than the large GCDs because of the Césaron's law on the GCD, which means that the high GCDs are very difficult to learn because you see so many examples of them. So what if we change that? Again, make it log uniform. Make it uniform doesn't work, but make it log uniform. Make, change, correct the balance. And this again is going to improve a lot your result. And you get into 90 GCD out, correct GCD out of 100. In fact, if you use, log uniform appearance and log uniform outcomes, you end up with about 91 GCD. If you use repeated examples and log uniform outcomes, that's my best result, you get to 99 GCD. So the question, can you learn the GCD? Yes, you can, but you really have to work for it. And this tells us a number of interesting things about how the model learns. You see that the model seems to learn by classifying its inputs, into groups of input with the same GCD, and then classifying the GCD. It seems that this idea that out of distribution, when you train on a different distribution and you test distribution is a bad idea, is wrong here. Because my best model, I'm trained on a distribution that is different on the distribution I test on, and it helps. So, and repetition is even more, controversial, because the idea that because you repeat the same example, it should work better is very unnatural, but it seems to work. So, what's very interesting is that you can see with this kind of math problem, a very interesting way to go by studying AI, because if you do language, you cannot do that. If you do language, you're stuck with the data you have, the data you scraped on the internet. Here, you're totally free of using, first, the theory you have on the GCD, and second, different ways of generating and testing it. Okay, just for the fun of it, you can get that, it's not specific to the GCD. So this is something you could see with multiplication modulo 67. So you got two large numbers, you multiply them, and you calculate the residual mod 67. If you train on random data, etc., between 1 and a million, no model learns. Everything is at 0. So it doesn't work at all. If you limit the data, so if you repeat data, you can see that the model learns. Some models achieve 100%. Even more interestingly, you can see that the results are quantized. So the model achieves certain performance and not others. So you have those kind of steps. And if you train on log uniform appearance, you can see the same thing. The model is flat for a moment, and then the curves learn 100%. So it seemed that my recipes for the GCD would work for other arithmetic problems. Okay, I think I'll stop there. Yeah, I'll stop there. Thank you very much.
Thank you, François. So, time for questions.
Yeah, thanks for the talk. I have a couple of questions about the first part, the Lyapunov functions. How do you know that the Lyapunov function that your model generates is actually a Lyapunov function?
So you have the free Lyapunov condition, infinity at infinity, 0, strict minimum at 0, and the Lyapunov value. So you need an external solver. So I should precise that. All this is predicated in the fact that you have a way to verify the solution, because the prediction comes with no guarantee. So here we use two methods. We had a sum of square minimization tool that we use, and we also use an SMT solver in order to do that. So linear computer algebra tool packages that we use for that. So they sort of work. Basically, we know that when the model says the Lyapunov function is a Lyapunov function, it's always true. But we know we have a couple of false negatives. So cases where the predictor doesn't work. We think it's about 5–7% for the tests we've done. We cannot do better than that. So bottom line is you always need a checker.
Right, but then my question is, because you do need a checker, and I'm thinking out the polynomial system, what's the advantage of just using SOS tools? Because you do need the checker afterwards. And SOS tool would generate so many other square packages.
Yeah. Yes, so the difference here is that the source tool is going to find you a Lyapunov function. We argue it's slower, but we can discuss that. It's not really important. The problem is that the source tool is limited to polynomial system. And we... Okay, so I would be ready to discuss that. My impression is the system is more general here than the source tool. And the idea here is that in general, so you couldn't solve problem like NPR problem with that, problem where you cannot verify. You have to be able to verify. And everything is predicated on the idea that verifying is much easier than finding the solution. If you have the same costs, then it's not worth it. But that would be the main idea. I'm happy to rediscuss the roles of those tools.
Precisely because you need to shuffle, right? Because you don't want to learn the solution from
Yeah.
data. You add certain functions and multiply and so on, right? Couldn't you do this also for the forward data? Like you generate a forward diagonal function, and then you add, say, some term which is orthogonal to the F.
Yes, yes.
To make them more.
Yes, you definitely could. You definitely could modify the forward function, the forward approach. In the case of, it's not crucial in that case, but you could add a constant, you could add something in order to make the problem a little harder for the machine or a little different or more general, and that would probably make sense. There's a deep difference though, because in the backward case, you really need to have the randomness in the generator if you don't want the model not to learn. So in the case of the forward, I agree. We had this in previous papers, notably the integration paper. The question was, when you integrate a function, do you want to simplify the function before you integrate or not? Do you want the model to have simplified function or not? Do you want to have 2x or x plus x is admissible, or 2x minus, or 3x minus x is admissible? And in the beginning, we said, oh, no, you need to simplify or the model will never learn. And one day we tried the other, and we noticed it didn't change. Of course, if you don't simplify, the search space is a little larger, so you will need more examples, but you will not have a major difference in accuracy. So the model doesn't really care. It's something that you notice, in language model is very clear. When you see what ChatGPT is trained on, it's trained on scraped internet. So the grammar should be horrible. The spelling should be abominable, and it's not the case. Everything that is easy is usually learned for free by transformers. So spelling, the order of words, correct sentence, this is learned very easily. So in that case, simplifying, knowing that 1 + 1 = 2, etc., will usually be learned for free in your training data. So, but yes, you could do it. I'm sorry, I can't hear you.
So it's a technical question. You had a graph where you were comparing performances between when you trained on 25 million samples, 50 million samples.
Yeah.
This called infinity. I was wondering, how do you measure for infinity?
How I what?
For infinite sample type.
Yeah. So the infinite sample, basically in this case, the infinite sample means that you generate a new data. So it's not exactly infinite in the sense. So here, my data is selected, my pairs of data for the GCD are numbered between 1 and 1 million. So there are 10 to the 12 possible data, and I train on 1 billion. So the birthday paradox is going to play here, and you will have a few duplicates, but very few. So the infinite data, basically, every time you need a new example, you roll 2 dice, and you get a new sample. Okay? So you see the infinity, it's a fake infinity. There's no such thing as an infinite data set. The idea is, what I call infinite is that pretty much all samples are randomly sampled from a phase space of 10 to the 12, knowing that I will never need more than 10 to the 9 example. So there will be very, very few collisions. So all examples are essentially unique. We actually did the calculation and noticed that it's about 500,000 examples that have been seen twice, and none, like way less than 1 that have been seen 3 times if you play the birthday paradox on that. So yeah, I agree. Infinite, maybe single use would be a better way to spell it. This is a good question. It's complicated, because the reason I want to use math to do that is that because in math I have more control on the data because I know the math. So I chose to do this on math because in math I can say, in language people try to do that, but they're very, very limited. They're limited, you've seen the studies, they're limited to different use of pronouns in different language, different use of gender in different language, and you translate and you see whether the model translates this word that has two meanings into one meaning, etc. But in language it's very, very artificial. In math it's easy to do. So yes, in order to do an analysis of transformer using math, the goal is to exploit the structure of math and all the possibility you have with generation in order to understand what the transformers are doing and in order to deeply understand what they're doing. If you understand nothing about the problem, then there's nothing you can learn from this. It will just be, oh my, I got 62% accuracy, and what do you do from it? So yes, the deep thing, but the funny thing is that, so the thing I haven't shown you was a recent work on the Collatz problem, 3n+1, which is a very complicated sequence. People lose their mind over it. And which shows that if you train a transformer to predict the future elements there, you don't try to predict whether it stops as 1 or not there, you can see that a number of very, very, very deterministic patterns happen in transformer. And so it's interesting because it tells us something about the way the model learns. The model classifies input, the way it learns regression in that case. So it's really different from, trying to solve pure math. The reason I'm interested in that, so I'm all for mathematical discovery, the reason why I'm doing that is that I think that if I can understand how the transformer computes and what the transformer learns, I will be able to modify the architecture or to improve the architecture to get something that is slightly more suited to my mathematical problem. The fact that transformers are bad at arithmetic is a problem. It's a huge problem because arithmetic is everywhere. So if you can have, the idea that, for instance, this idea that if you change the operand to have a log uniform distribution of operands, which seems to work in many cases, this is something useful because it means that when I generate Lyapunov function, for instance, the prefactors, which might be integers, I might want to use a log uniform distribution for them because I learned it from here. So that's the general, that's the philosophical motivation for the way I do that. It happens also to be useful for other activities, and this pleased my masters at Meta. Obviously, they want results that are not specialized for math. But yeah, the real philosophical reason is that if you want to do AI for math, you have to understand how the easy math are learned in order to try to take advantage of this to do the hard math. Yep.
Yes. Thanks a lot for the nice talk. I just have a general question. In fact, I've seen in a slide that you say that you managed to find some counterexample for some old pure math problem. So my question is just kind of a general question. Did you discuss with the community related to this kind of problems, and how did they take it? Were they very interested, and do you think that was like an inflection point?
Okay, that's a sociological question, but that's a good one. Actually, the person who did that was Adam Wagner, who is a mathematician. So he was one of the few mathematicians in 2021 that was interested in that. So to be very honest, the first papers we had with Amaury, etc., we had reviews, and you could spot a serious mathematician in the reviewer in the fact that I don't believe it. And you could say anything, I don't believe it, sometimes with very bad mathematical argument, but that was very typical. So 3 or 4 years ago, people would not believe this existed, or would say you probably cheated, or there's something, Now, the results, like the results from Adam and all that, show that, okay, we are not able to solve any problem, but there are specific classes of problems, like those conjectures, which are probably false, and you want to find a counterexample that can be attacked. In that case, the honor of the mathematician is also safe, because the one who discovered the counterexample is not the machine, but the mathematician. Whether the mathematician or the machine did most of the job, I'll let you decide. But at least, the honor is safe. So starting from there, and with the work of others, DeepMind have been pushing lots of new things, less multiplication in the Strassen algorithm or stuff like that. there's been a growing interest from the pure mathematical community. So to give you an example, last year we organized a 2-month seminar, a 2-month program in Harvard, where we invited really all kinds of mathematicians in all areas. And there were AI people, and there were really quite a few of them then working on it, and quite a few papers were published. In September, we have yet another of those meetings with mathematicians and AI people in Oberwolfach, and the MFO people were quite excited by this. So I would tell 2 years or 3 years ago, this was impossible. I can promise that. So I think so you still got people who say, oh no, I don't want to be replaced, etc. But there are many mathematicians that are really interested in this. And I can't help noticing that, in the past, you needed to convince people, etc. And now you get mathematicians coming to you and say, okay, I have an idea, I got the postdocs, let's try. And so it's, I think it's moving. What we don't quite know yet is how far this will extend. It's clear that in some areas it's easier to do progress than in others. There probably are whole areas that will be solved, if you like. I think combinatorics, a lot of problems in combinatorics are only hard because we don't have the time to work on them. And if we have those tools that give you good solution and good intuition, etc., we'll discover that a lot of problems cease to be problems. Just like, a century ago, it was the job of mathematicians to compute the decimals of pi. Gauss did that. Now we don't do it anymore. We've got machines. The same is going to happen there. What is less clear is, where can you use it? And this is where creativity starts happening in the mathematical community. People discover new ways to use AI to help them. And this is not known. One thing that is surprising, though, here is that AI works in ways we wouldn't think in. In all the example I provide, especially in the Adam Wagner example, or the pattern boost example, AI works as a help to creativity. And this is surprising. We wouldn't expect AI to help creativity. We would hope it to help, calculation and big calculation and stuff like that. In this case, no. It suggests ideas you wouldn't have. And so this is one of the surprising things. Yeah.
So technically, I wouldn't really know how to do this, okay, but one can try to enforce exactly what multiplication is on one side, and then use the transformer to learn things connected to it or something like this.
I think there are several ways to answer that. So why use transformers now? The main reason to use transformers now is everybody is doing transformers. Right. So if you don't want to, I would love to use graph neural networks or ConvNet and all that. The problem is that there are like 5 papers published in GNN every year for, I exaggerate, by 5 papers for 1,000 transformer papers. So with the transformer, you get all the others to work for you. So if architecture is not the thing you're interested in, also transformers tend to have a lot of, they've proven to be extremely adaptable. So they've been used everywhere, not because we didn't have better ways to do it, but because if you have enough data, you can use transformer for anything. So it's sort of practical. It's maybe a lazy solution, but it's sort of practical, and it's a good idea if you want to leverage the work of others. Another way to think of it on different architecture, so I completely agree with you that the way transformers were designed for language, and they were optimized for language. And it's quite possible that inside the transformer architecture, there's a number of tricks that we have introduced so that we would better perform at language, and these tricks might be detrimental to math. So it's quite possible that, small improvement of the architecture might help. I would love to do that. I think it's a complicated thing because it's a lot of work, to measure the impact. There are many wild parameters in the transformer. There are many ways to change the architecture. So there's a question of how much compute and how much time you have. This said, with the mathematical, AI for math community growing, I wouldn't be surprised. The only problem is that academics usually don't have GPUs, and you need GPUs to test hypotheses. But with this exception, I wouldn't be surprised if people started, maybe not developing brand new architecture, but improving the transformer architecture to do better arithmetic or better math. The only limitation to that is that some people have been doing that for addition and multiplication. They change the positional embedding so that. But the problem is that if you change, an element to adapt to really the specific of the one problem you are solving, you're not achieving anything. You can do better addition if you use a specific thing that uses the properties of addition, but it will work only on addition, and you never want to do only additions. So, yeah.
Probably we are in different fields of science, in particular in different fields of mathematics, and listening to this, I could say, well, yeah, it works for Lyapunov, it works for the GCD, but will this work in my area? So what can you say in general about I don't know, I was just thinking,
Yeah, I was.
you teach to the students calculus. Calculus is full of inequalities. So, will I be able to discover new inequalities with this?
Well, I think so. I think the whole problem, it's an experimental science. So, they say in science the problem is finding the questions. In experimental science, the problem is designing an experiment. How can you design an experiment to test your ideas? I've been quite surprised with mathematics because there are areas, I would never have bet you could use this in groups. Because, groups are very discrete, but what do you want to do, learn in groups? And I'm currently working on, representation of braid groups or representation of infinite groups. And we're very close to discovering, we're close to open problems on this. And all it took was a couple of specialists who really wanted to try it. I've seen people working on Kelly graphs, so again, groups, etc. And it took only one guy who was interested enough. So there might be places where there are contraindications, but I have the tendency to observe that, why do we apply it to Lyapunov function? Because Amaury knew Guillaume Lample, who was my first co-author. They were in school together, and Guillaume told Amaury, and Amaury said, I have an idea about generating Lyapunov function, which was the beginning, a very, very bad version of the generator. And this is how it started 5 or 6 years ago. So usually I notice that it's more someone from a field being interested by AI that caused the AI to develop to this field than a specific property of the field.
So, for instance, I have a system of differential equations that I see interaction of different species. If I give it to you, will you be able to tell me whether there is a Lyapunov function? Because I tried, I never found one. But when I draw simulations, I have the impression that the system is very stable.
So we could definitely try, the trained model.
Yes.
And push it. It's something we want to do.
So what are the dimensions? Do you care about the dimension of the system?
It should not. Well, the thing is that the dimension has to have been seen in the training data. So if we use the model we train now, 5 dimension or 6 dimension is the max we can do. If we add more dimension, we will need to generate more data, so that will take a week or two. But that and retrain a model. But
did you ever try to see whether this tool that has been trained for dimension, say, 5, will be able to do something with dimension 25?
No, it won't.
It won't.
It won't, but priming might work. You might just need to give it a few examples and it will. Maybe 5 to 25 is a bit violent, but 5 to 7, I'm sure with just a few examples it would work. It's not incredibly difficult to train. Generating the data might take a few days. Training the model will take a few more days. So in a week, you can have a model working on that. Okay, you might need a meta GPUs or stuff like that, but it's honestly, it's doable. So, no, one thing we want to do is to try on, interesting data. One thing we did, it was, I didn't mention, that Amaury teach a course on the Lyapunov function in École des Ponts. So we tried to see how good were students master students after one semester on the Lyapunov function. And their accuracy is 9%, whereas 84 for the model. So we were sort of happy with that. But to be honest, I think you can, we want to try on actual data on, Amaury needs to provide me.
And what about a simpler, or at least related to the differential equation, a problem that looks simpler? I give a function, I give a solution, I would like to know what the differential equation is. Can it be done?
So actually some people try to do this for ODE, because there's an area, I got 2 papers on that, but there's an area that's unfortunately not studied enough, which is called symbolic regression. So symbolic regression, you give a set of data, say in high dimension, x and y, and you want to find a function that goes through. So typically this used to be done with genetic algorithm, and a couple of years ago, several teams, including ours, showed that you could use transformers to do that and achieve decent values. So after doing that, some people have said, okay, it would be even more interesting, I give you trajectories, please find me ODEs that verify. So there was a paper, I think it's called ODE former, like transformer. Not absolutely sure who wrote it. I sort of remember they were Swiss, but can't remember where. But there's a team that worked on that. I don't know if there were many follow-up. This is a very slow-moving area because not so many people, but yes, this would be doable. The question is, what do you want to learn? Would it be easier to try to learn the ODE or some conserved quantity or some property, etc.? But yeah, judging from previous experiment, this could work. This definitely could work.